So good day to everyone. Today I'm going to present about Laplace transforms, and without any further ado, let's get into the topic. So Laplace transforms. What are Laplace transforms? The Laplace transform of a function f of t is defined to be as follows. So the notation that we use is capital F of s, which is defined as the stylized capital L of the function f of t equal to the integral from 0 to infinity of the function f of t times e to the negative st dt. So there are actually a couple of conditions for the Laplace transform of a function to exist. So the two conditions are as follows. So number one, f of t has to be a piecewise continuous function on the interval 0 to infinity. And the second one is that f of t has to be of exponential order. And by this, I mean there must be constants alpha, capital M, and a particular t value, t sub 0, such that the modulus of f of t must be less than or equal to m times e raised to the alpha times t for all t greater than or equal to t sub 0. So these are the two ingredients that a function has to satisfy so that the function will actually be defined of its Laplace transform. Okay, so let's try to give some examples of how to compute for the Laplace transforms of basic functions. So examples. So number one, so determine the Laplace transform of the constant function f of t equal to c, where c is a constant. Okay. So for the solution, the Laplace transform of the function f of t equals c will be, so this is we're using the notation now, so L of c is the same as the integral from 0 to infinity. So I replace f of t by c and write beside it e to the negative st dt. And what happens here is, since c is just a constant, I can bring it outside the integral. And so this is just equal to the following integral. Incidentally, the integral of e to the negative st is negative 1 over s times e to the negative st integrated from 0 to infinity. So this becomes c times some expression. So this becomes limit as t goes to infinity of negative 1 over s times e to the negative st, okay, minus 1 over s e to the negative 0, okay, after plugging in t equals 0 into the expression. And so this becomes c times limit of negative 1 over s times e to the negative st as t goes to infinity plus 1 over s. And if you will notice, the term negative 1 over s times e to the negative st, so negative 1 over s e to the negative st is just equal to negative 1 over s times e to the st. Okay, now we need to impose some kind of condition on the values of s. In particular, s should not be equal to 0 because the s here will be located in the denominator of the fraction. And furthermore, because it is the coefficient of the power of e, and we have a negative sign in front of the st, we have to make sure that the value of s is positive. Otherwise, if s is negative, then this expression will actually be undefined as t goes to positive infinity. So as long as s is greater than 0, then we will be able to evaluate this limit. And in fact, we have the license to say that as t goes to infinity, this expression here goes to 0. And this is what's happening as t goes to infinity. This will disappear. Okay. And the answer that we get in the end is simply c over s, on condition that, again, s is positive. So the Laplace transform of the constant function f of t equals c is equal to c over s as long as s is positive. So this is true, for example, if we want to evaluate the Laplace transform of the constant function 7. So this should be equal to 7 over s. The Laplace transform of negative 3 over 2 is equal to negative 3 over 2 over s, or negative 3 over 2s. All right, so that's good. And I hope that's clear. I want to give an example now which involves some kind of polynomial term. Okay, so let's try to evaluate the Laplace transform of t squared. Now, again, by definition, the Laplace transform of t squared should be equal to the integral from 0 to infinity of the function t squared times e to the negative st dt. So what we do now is we try to determine the antiderivative of the function t squared times e to the negative st. And to be able to do that, we wish to do integration by parts. And so by integration by parts, we let the function u be equal to t squared and the function dv, or the differential dv, equal to negative st dt. This should give du be equal to 2t times dt, and an antiderivative of e to the negative st will be negative 1 over s e to the negative st. So that we now go back to our original integral, which is by an application of integration by parts, we will get negative 1 times t squared, okay, over s e to the negative st. Okay, so it's just the product of this and this minus the integral v, so negative 1 over s e to the negative st. So v du, which is 2t dt. This in turn is equal to negative t squared over s e to the negative st, and then we have plus 2 over s times integral of t times e to the negative st dt. And we're not quite done yet because we have to integrate the function here, which is t times e to the negative st. And to be able to do that, we need to apply again integration by parts. And similarly, what we do is we let u be equal to t, dv, the differential, be the same thing, e to the negative st dt. And this should imply du is equal to dt, and v should still be the same quantity, negative 1 over s times e to the negative st. So let's put a demarcation here. This will become equal to negative t squared over s times e to the negative st plus 2 over s times some expression which is equal to negative t over s e to the negative st minus v, which is this, negative 1 over s e to the negative st du, which is this, so that is just dt. And then we close the expression. So this is equal to negative t squared over s times e to the negative st minus 2t over s squared times e to the negative st. And we have minus 2 over s squared times integral of e to the negative st dt. So there's still one simple integral we need to evaluate, but this should be straightforward, so that in the end what we get is let me correct this, this should be plus, because we have a minus here and then another minus here. All right, okay, let me just clean this up a little bit. Okay, so there must be integral here. So because we have minus minus, so we bring out the 1 over s, so that we get here in the next line plus 2 over s squared. And this in turn is just negative 2 over s cubed times e to the negative st. Okay. So good. And now we are ready to evaluate the Laplace transform for the function e to the negative st. In fact, let me change the color of the ink. Okay, so this will become negative t squared over s e to the negative st minus 2t over s squared e to the negative st minus 2 over s cubed e to the negative st, which is integrated from 0 to infinity. Okay, so let me bring the calculation now to this side of our notepad. So this becomes, so let me call this star. Okay, so star will just be equal to the following. So limit as t goes to positive infinity of negative t squared, so this should be negative t squared over s e to the negative st minus 2t over s squared e to the negative st minus 2 over s cubed e to the negative st. Okay, and then we plug in the value t equals 0 into the expression, so that this becomes 0 plus 0 plus 2 over s cubed times e to the negative 0. So this again is after we have plugged in t equals 0 into the expression. And this is equal to limit as t goes to infinity of still the same expression, so negative t squared over s e to the negative s squared minus 2t over s squared e to the negative st minus 2 over s cubed e to the negative st, and then here we have plus 2 over s cubed. And so we evaluate the limit expression, and the one good thing about the expression is if you want to evaluate this limit, then we can actually take advantage of using L'Hopital's rule. And so I will assume at this point that you have heard of it and you have applied it once in the past, at least once in the past. And you will find out after doing this that the limit as t goes to infinity of the given expression is equal to 0. So that the entire thing will be equal to 2 over s cubed. Again, the assumption here is that since we have powers of s in the denominator, we want to make sure that, number one, s is not equal to 0. And secondly, s should be positive. Okay? So this is going to be true as long as s is positive. So therefore, the Laplace transform of t squared, okay, will be equal to 2 over s cubed, given that s is positive. So let's highlight that. All right, so I hope that is clear. And interestingly enough, this example has a generalization. In fact, if you are trying to consider the Laplace transform of the general polynomial term t to the n, which is by definition equal to this, then by induction, it can be proven that the Laplace transform of L of t to the n is no other than n factorial over s raised to the n plus 1. And you can verify directly, in fact, this formula when you try to go back to the example number 2, where n is equal to 2. Okay, so we get answer. So we get the answer in number 2 if n is equal to 2. Okay, and in particular, if say if you want to evaluate the Laplace transform of t to the fifth, then this will just be equal to, let's see. So let us do the substitution right away. So this will become, so this becomes 5 factorial over s raised to the sixth, which is equal to 120 over s to the sixth. And if you want to consider the Laplace transform of t to the seventh, for example, then you will have 7 factorial over s to the eighth, which is equal to 5040 all over s to the eighth. Okay. All right. So so this is the Laplace transform of the polynomial term t to the n. And another example I would like to get into tells something about a very useful property of Laplace transforms. And that property is no other than linearity, which basically says that the Laplace operator, the Laplace transform, is linear. And in more precise terms, linearity is actually given by the following equation. So the Laplace transform of a times f of t plus b times g of t will be equal to a times the Laplace transform of f of t plus b times the Laplace transform of g of t. Okay, and so let's try to give a particular example to this. So for example, L of negative 5 t cubed plus 3 over 2 t squared minus, let's see, so minus 3t plus 10 will be equal to the following. Negative 5 times Laplace transform of t cubed plus 3 over 2 times Laplace transform of t squared minus 3 times Laplace transform of t plus the Laplace transform of 10, which, by applying the general rule that we have stated in example number 3, this will be equal to negative 5 times 3 factorial over s power 4 plus 3 over 2 times 2 factorial over s raised to the third power minus 3 times 1 factorial all over s squared plus 10 over s. And it is noteworthy to indicate the fact that this will actually be true as long as s is positive. So simplifying, this becomes 3 factorial is 6, so times negative 5, so that's negative 30 over s4, plus 2 factorial is 2, so we have 3 over s cubed. And then 1 factorial is just equal to 1, so this becomes 3 over s squared. And finally, the last term, we have 10 over s, where again, we assume that s is positive. And this is the Laplace transform of negative 5t cubed plus 3 over 2 t squared minus 3t plus 10. Okay. And this is it. Okay. So the next example I want to give focuses on another type of elementary function. So let's try to find the Laplace transform of f of t equal to e to the at, where a is a constant. Okay. Okay, let me write this out more clearly. Okay, so for the solution, the Laplace transform of e to the at will be equal to the integral from 0 to infinity of e to the at times e to the negative st dt. If I do a little bit of combination of the exponential terms and a rearrangement of the powers of the base e, then what we get is the following. So we are considering the integral from 0 to infinity of e raised to the negative quantity s minus a times t dt. And this is because of the fact that, okay, so let's try to focus on that. So e to the at times e to the negative st is e raised to the at minus st, which is equal to e to the quantity a minus s times t, which is the same as e to the negative quantity s minus a times t. Now, we are writing it this way because what we want to do is, or what we want to have is for this integral to converge. And this integral will only converge or will have a finite value if we ensure that s minus a is greater than 0 or s is greater than a. So we want to make sure that the integral will actually have a finite answer by letting s be greater than a. Otherwise, if s is less than or equal to a, then the integral will not have a finite value and it will be undefined. Okay. So that said, we can now focus on evaluating the integral. Incidentally, it's quite easy to get the antiderivative of this integrand. So it's just negative 1 over s minus a integrated from 0 to infinity. This in turn is equal to the limit as t goes to infinity of negative 1 over s minus a times e to the negative s minus a t minus 1 over s minus a, and then if we plug 0 into the exponential term, we will have e to the negative 0. Incidentally, that will just be equal to 1. So we have limit as t goes to infinity of negative 1 over s minus a times e to the negative quantity s minus a t plus 1 over s minus a. And what we can do here, if we want to evaluate the limit as t goes to infinity, is to express e to the negative s minus a times t as 1 over e to the s minus at. And since s minus a is positive and t goes to positive infinity, this term will definitely goes to 0 as t goes to positive infinity. So that this limit expression here will be equal to 0, and in the end what we get is 1 over s minus a. And this is always true as long as s is greater than a. So again, to recap, the Laplace transform of the exponential function e to the at is just equal to 1 over s minus a, which is true as long as s is greater than a. For a concrete example, we can give the Laplace transform of e raised to the 2t will be equal to 1 over s minus 2, while the Laplace transform of e to the negative 3 over 2t will be equal to 1 over s minus minus 3 over 2, and that becomes 1 over s plus 3 over 2. Okay. In the first Laplace transform, we have to make sure that s is greater than 2, and in the second one, we have to make sure that s is greater than negative 3 over 2. Okay, and so that's it. Okay, so I want to go now to one last example, just to have a recap of what we have done. We have defined the Laplace transform of a function. We have determined the Laplace transform of a constant function, as well as that of a polynomial function. And we also found out that the Laplace transform is actually linear when we are considering linear combinations of functions. And finally, in the last example, we have determined the Laplace transform of the exponential term e to the at. All right, so for our last example, let's try to do the following example. So find the Laplace transform of f of t equals sine of a t, where a is a constant coefficient. Okay, so just like before, we apply the definition of the Laplace transform. So L of sine of at is equal to the integral from 0 to infinity of sine at times e to the negative st dt. And before we can actually evaluate the definite integral, what we want to do is to first find out what exactly is the indefinite integral of sine of at times e to the negative st. And the means by which we determine that is again by integration by parts, where we let the function u be equal to sine of at and dv is equal to e to the negative st dt. This will imply the following. The differential du will be equal to cosine at dt, and by application of chain rule, we put an a in front of the cosine. And similarly, v here will be e to the negative st, and by reversing the process chain rule, we throw in the negative 1 over s in front of e to the negative st. So that by using the template for the integration by parts formula, we have negative 1 over s e to the negative st times the function u, which is sine of at, minus integral of the function v, which is negative 1 over s e to the negative st. So v du, so we have an a here, so times a cosine at dt. And then let's put some demarcation line here. So this will be equal to negative 1 over s e to the negative st sine of at. And then we have a minus here and a minus here and the coefficient a here. So we have plus a over s times the integral of cosine at times e to the negative st dt. Okay. Now, incidentally, we still have an integral which we need to evaluate, and most likely we have to use integration by parts again on this integral. Okay. So what I'm going to do is, so I'm going to denote this integral by a green strip of ink, and so the green strip of ink will actually be equal to some expression. Okay, and to be able to do that, what we can do is, again, we have to use integration by parts. Okay, so by using integration by parts on cosine at e to the negative st dt, we let u be equal to cosine of at and our differential dv as e to the negative st dt. From here, we have du is negative a sine of at dt, while v, on the other hand, is negative 1 over s is the negative st. So that this will become u times v, so negative 1 over s e to the negative st cosine at minus integral v, which is negative 1 over s e to the negative st times the differential du, which is negative a sine at dt. And again, let's put a demarcation here so that this becomes negative 1 over s e to the negative st cosine at. Now we have a minus 1 over s here and a minus a here, so this becomes minus a over s integral of sine at times e to the negative st dt. So that if we go back to our previous integral, this will just become negative. So negative 1 over s e to the negative st sine of at plus a over s, and then we have a parenthetical expression here, which is this expression. Okay, so this becomes negative 1 over s times e to the negative st cosine AT minus A over S times integral of sine AT e to the negative ST dt, and then I close the parenthetical expression. And what I'm going to do is, okay, I'm going to bring the calculation on this side. Okay, so I'm going to leapfrog our previous calculation of the integration by parts and continue with the calculation here. So let's put a demarcation line here. So this becomes okay. So this becomes equal to the following. So this is negative 1 over S e to the negative st sine of AT, and then I can actually distribute A over S. So you see the A over S here to the terms inside, so that what we get is the following. So negative A over S squared times e to the negative st cosine of AT minus A over S squared times the integral of sine AT e to the negative st dt. Okay. But take note that this is actually equal to the definition of the integral that we actually was considering here. So it's actually this integral. Okay, so this is just integral of sine, oops. So this is equal to sine of AT times e to the negative st dt. And the good thing here is we can transpose this term to the other side of the equation. If you will notice, this term here on this side of the equation and this term here contains the common term of the integral of sine of AT times e to the negative st. So what will happen in the next line is this will imply that integral of sine of AT e to the negative st dt plus, okay, all right. Let's try to see if, let's see. Okay. So everything is good so far. So we have, let's see. So let me have a little bit of correction here. So we have A over S here. I should, if people notice here, I have an A here and an A here. Okay. And so what I should get here is I should put a 2 here. Okay. All right, so that should be good. And so going back, we'll have A squared over S squared times integral of sine AT times e to the negative st dt should be equal to negative 1 over S e to the negative st sine of AT minus A over S squared e to the negative st cosine AT. If I combine these two terms containing the integral sine of AT times e to the negative st, what we will get is 1 plus A squared over S squared times integral of sine at e to the negative st dt is just equal to this on the right hand side. So with this in mind, we are almost done. Okay, this in particular implies that 1 plus a squared over s squared times the definite integral from 0 to infinity of sine of at e to the negative st dt will just be equal to this expression integrated so again, as I was saying, it's just this expression integrated from 0 to infinity. And we will be able to find out that the expression on the left hand side will be s squared plus a squared all over s squared times integral from 0 to sine at e to the negative st dt. By applying L'Hopital's rule, we will find out that the right hand side of the equation will be equal to 0. So it will be negative 0 minus 0 plus 0, because when we plug in t equals 0 for sine of at, the value is 0, plus a over s squared, then e to the negative 0 times cosine of 0. This gives us a over s squared, and this is true as long as s is, again, positive. So it implies then that s squared plus a squared times the integral of sine at times e to the negative st dt is equal to a for s, which is positive. And so that in the end, what we will get is the integral from 0 to infinity sine of at times e to the negative st dt will be equal to a over s squared plus a squared, as long as s is positive. And incidentally, this thing here, the left-hand side of the equation, is none other than the Laplace transform of sine of at. So we make the conclusion that the Laplace transform of sine of at is equal to a over s squared plus a squared, as long as s is positive. That ends our last example for this presentation.